Hello, and welcome back to General Chemistry 2. My name is Daniel, and in this video we're going to be starting to look at nuclear chemistry. First off, we're going to define what exactly a nuclear reaction is as opposed to just a standard chemical reaction. And then we'll look at how we can balance them and also the kinetics and thermodynamics that apply to nuclear reactions. And then at the end of the video, we'll look at the applications of nuclear reactions in energy, in particular with nuclear fission and nuclear fusion and some other applications. So first off, let's define a nuclear reaction. So we know that in a chemical reaction, we have the changing of molecular species. So if we have, let's say, a combustion reaction of methane, something like that, so here we see we're just changing the bonds within all of these different chemical species, but all the atoms are the same on both sides. On the other hand, in a nuclear reaction, we have elements changing into other elements. So we can have something like uranium-238 changing to, let's say, thorium-234, or something like that. So that's what distinguishes a nuclear reaction. We have a change in the identity of the elements that are taking place in a nuclear reaction. And the reason for that is because of the decay of protons and neutrons, this changing of the number of protons and neutrons within the nucleus of each species. So since this is the case, since we're transmuting elements, changing them into different things by changing their nucleus, nuclear reactions have extremely high energy compared to normal chemical reactions, as we'll see later in the video. For now, let's look at the different kinds of nuclear reactions. So there's three generally basic reactions that can occur. The first one is the decay of something. So if something is if we have an unstable nucleus, it can decay into a more stable nucleus by emitting some kind of particle. And you can see that in this scenario, our number of protons has changed from 84 to 82, and our number of neutrons has also changed. We have a mass number of 212 going to instead to 208. We can also have the capture of something. So we can have a species capturing some kind of particle, and that will also change its number of protons and neutrons. And then finally, we can have something called transmutation, where a particle absorbs something, or a nuclide absorbs some kind of particle to form a new species that then releases another different kind of particle. But what you'll see here is that what's like for all of these is that the number of neutrons and the number of protons is changing within each species produced. So now let's look at the kinds of particles that can be involved in a nuclear reaction. These are called elementary particles. They're the things that are released or produced or captured in nuclear reactions to change around the mass number and the atomic number. So the first most common one is what's known as the alpha particle. You sometimes see that as the sign alpha, which looks like something like this. This has the same configuration as a helium nucleus, meaning it has a mass number of 4, atomic number of 2, which means 2 neutrons, 2 protons. So when we produce an alpha particle, that means that the mass number has decreased by 4. That's a change in A. And then the atomic number has decreased by 2, which is synonymous with losing 2 protons. So that would look something like this. If we have some species with a mass number of 100 and an atomic number of 50, and it releases an alpha particle, the new species that's produced is going to have 4 less for its mass number, so it would be 96. And it would have 2 less for its atomic number, so that would be 48, and whatever that corresponds to. So that's what we mean by the change in A and the change in Z. This new species produced has 4 less mass number and 2 less atomic number. The second common elementary particle is the beta particle. That's represented either by a beta, or you can also sometimes see it as just an E. And the reason for that is because it has a similar configuration to an electron. You see that it has essentially no mass, and it has a -1 charge as opposed to a proton's positive charge. So if we did the same thing for this species, the particle X, if we took that and produced a beta particle instead, we see that to balance out the numbers here, we'd keep the same mass number, but have 1 extra for our atomic number. And now you see that the numbers on each side are balanced. So that means that when we produce a beta particle, we have an increase in Z of +1. And obviously that's going to make the ratio of neutrons to protons decrease, because now there's more protons. The other less common but still sometimes used elementary particles are positron production. A positron production is essentially the same thing as a beta particle, except now you see it has a +1 for its atomic number. So it's going to do the opposite for Z. Then we also have electron capture. Recall from this slide here that when we have a capture of something, that means it's in the reactants. So if we did that down here, let's say we had the electron capture in this element X, that would cause us to have the same mass number and a lower atomic number on the right side. And so you see that positron production and electron capture essentially cause the same thing to happen, a decrease in the atomic number of 1. And the other common elementary particle is the gamma ray, although we're not going to talk too much about that. A gamma ray is just basically it's almost this kind of massless and chargeless species. It's really only produced to release energy from a decaying system, but it doesn't really affect the stoichiometry of the reaction itself. Okay, so those are the most common elementary particles we'll run into. We'll also see sometimes neutrons. So a neutron, as you know, is chargeless but has a mass number of 1. So a neutron would just look like that. So that's the formula you might see for a neutron. Let's talk about what we mean, what's important about this changing neutron to proton ratio. We put it in the table. Let's see what it's actually important for. So what we see on the left side here is something known as the belt of stability. Basically, the dark dots that you see here in this line are these stable particles. The lighter dots are unstable particles. And then we have these two regions above the belt of stability and below the belt of stability. So what's important to note is that in general, for light elements, something like in period 2 or 3 or something like that, the most stable ratio of neutrons to protons is a 1-to-1 ratio. That's why we have things like oxygen 16, nitrogen 14, things like that. As we increase the size of the nucleus, we can have stable isotopes with further and further higher neutron to proton ratios. You see here for mercury that mercury has a mass number of 202, a atomic number of 80, and that gives us a 1.53 to 1 neutron to proton ratio. And that's also a stable species. So in general, as we increase the size of our nucleus, we can deviate from that 1-to-1 ratio that we see in the lighter elements. And that's basically what you're seeing in this, this graph on the left side here. So what we can see then is there's two kinds of scenarios for unstable particles. An unstable particle would either be above this belt of stability, or it could also be below the belt of stability. Down here we have too many protons. That means our ratio is too low. And then up here we have too many neutrons. So our ratio is too high. So any kind of unstable isotope will have one of these two extrema. It'll either have a too high neutron to proton ratio or a too low neutron to proton ratio. So the reason that we looked at the change in the neutron to proton ratio here is that we can use that to estimate how an unstable species will decay to form a more stable species. what you see up in this section with too many neutrons.